So this exercise is related to electric field and the capacitor structure questions. Either the structure question related to the exercise. So about 16 questions I have already discussed. I will share that recording and we'll start with question 17. Question 17, 2 point charges are there. When we say it's a point charge, it means the size of a charge is negligible as compared to like when we say a point charge, so we can ignore the size of the charge. So 2 point charges are there, 3.1 exponent minus 9 coulombs and minus 2.4 exponent negative 8 coulomb are placed at a distance of 0.03. So the distance between the charges is same as the distance between their centers. If the point charges we have, so means this distance is 0.04 meters, 43 meters. And one of the charge that is 3.1 into 10 to the power negative 9. And the other charge is minus 2.4 into 10 to the power minus 8. Calculate the magnitude of the force between the charges. So whenever two charges, either they attract or repel. So according to a Coulomb's law, that the force of attraction or a repulsion between the charges is given by K Q1 Q2 over R square. Means it's the force of attraction between them is directly proportional to product of the charges and inversely proportional to square of the distance between them. So we just substitute the values. What is the value of a K? And it's in a vacuum. K is actually equals to 1 upon 4 pi epsilon. And in a vacuum, when we substitute the value for epsilon, the permittivity of a free space, so we get the value for K, which is 9 exponent 9. So value of a K, you will take as 9 exponent 9. And the product of the charge, one of the charge is 3.1 into 10 to the power negative minus 9 coulomb. And the other one is negative. The negative sign is only showing like minus 2.4. It shows the nature that it is opposite, like the two charges are opposite. So they will try to attract each other. So 9 exponent 9 or 8.99 exponent 9, that exact number is 8.99 exponent 9. Or you can substitute 9 exponent 9 in place of K. The product of the charges, so 3.1 into 10 to the power minus 9 and 2.4 into 10 to the power negative 8. We did not take the negative sign here because we are finding the magnitude. So if we are finding a magnitude, we don't have to take the sign. We just need the value of the force and divide it by the square of the distance between the two charges, which is 0.043 meters. So this will be square. So when we simplify, we'll get the value of the force, the magnitude, which is 3.6 into 10 to the power minus 4 Newton. That is the force between the charges. The diagram represents the electric field around the 2 point charges. A is a positive and B is a negative charge. State what is the meaning of electric field strength. So, so the term electric field strength is refers to force experienced by a unit charge. That's a standard definition. That or to be more specific, you will mention electric field strength is a force acting on unit positive charge. Because the direction of electric field is always a direction in which the positive charge experience a force. So force on unit positive charge, that is known as the electric field strength. By considering the electric field at X due to A and due to B, explain the direction of electric field at X. So what will the direction of electric field? A, they mention it is a positive charge, and B, they mention it is a negative charge. So direction of electric field is out from positive and into negative. So if we draw this, So you can see it is out from A, like away from A, and it is into B. So when we write the answer, the structure, because we have to explain. So at X, what will happen? The positive charge experience a force due to, like, this positive charge is there at point X, it will experience a force away from A. And at X, the electric field due to A, we can say it is in the direction of AX. And same way, the at X, the positive charge, if there's, because at this point there's a positive charge placed. So this positive charge experience a force due to B towards B. And then as you can see here, the two forces at this point, the direction will be perpendicular to, so resultant force will be there in the direction of A to B. Like this will be the direction of the force, and this will be the direction of the force. So this is the direction of the force and this is the direction of the force. So when we combine these two electric field example, one is from due to A to X, another one is from X to B. So when we combine this, what we'll get a resultant direction, the resultant from tail of the first to the head of the last, that will give us the resultant direction. So the resultant force will be from A to B. So direction of electric field on the positive charge, it's out like or into or towards X, and it is out from X towards B. And what is the resultant force? The resultant of these two forces will be from A to B. Is it clear? Any doubt in this part? Okay. And what if two charges were oppositely, like example, if identical charges are there, so they will try to repel each other, try to cancel out the effect of each other. So in that case, we'll have no electric field in this region. Like the pattern will be different as compared to what is drawn. If A and B are the identical charges, so the pattern of the electric field. So if point X is here, if it is not and the electric field, so it means it will not experience any force. What if A is negative and B is positive, then the direction of electric field will be opposite. If A was negative and B is positive, so in that, and X is also unit positive, so the direction of electric field will be like this. So in that case, one is from B to X, another one is from X to A. So the resultant is from B to A. So in this case, the resultant will change. It will be from B to A. How we know the charge at X? Because whenever a question, the standard definition of electric field is it is the force experienced by a unit positive charge. So if there's a positive charge, which direction this will experience a force, that is called the direction of electric field. So this charge will always be positive because it is defined only for the positive charge, the direction of electric field. And if we work out the direction of electric field on a positive charge, for a negative charge, it will be opposite. So because the electric field is only defined for positive charge, that's why we can see the X is always positive until unless they mention in the question. So this was a 4 marks. So how you get the 4 marks? 1 mark you'll mention. If X was near, if point X, like at this point, the direction of electric field, you can consider this way, or if you consider the total like a for a, so that is a resultant. But if the point X was not in between, the point X was here. This was a point X. So, and it is a positive, A is positive and B is negative. So the direction, it will be in this way due to A, and the direction of a field or attraction due to B in this way. So as a result, when these two will combine, the resultant force will be in this direction. But specifically at point X, because the field was curvature, so from A to X, it was a line like this, and from X to B, the line like this. So when we combine them from A to X and from X to B, so we got a straight line. So the resultant is from A to B. The direction of the resultant will change as the position will change. So if the point X is midway, then the resultant is from A to B. But if it is from at this point, then the resultant is not, we don't get a resultant from A to B, because this is the first vector, this will be the second vector. So resultant is from tail of the first to the head of last. So when we combine these two, we'll get the resultant. So resultant will be making certain angle with the horizontal. Is it clear, the concept? In question 18, the photograph shows a digital Coulomb meter which measure the electric charge. As you can see, it's written 0.26 nanocoulomb, means 10 raised power, and negative is there, so 10 raised power minus 9. The charge of a Coulomb meter is stored on a capacitor inside a meter. A voltmeter inside the Coulomb meter measure the potential across it. This value is converted so that display shows the charge in nanocoulomb. Why the voltmeter must have a very high resistance? So this is a very common question in electricity, that why we prefer to use a voltmeter with a very high resistance, because if you read the question, we have a capacitor is there, the charge on a Coulomb meter is measured, how much stored on the capacitor. So if a voltmeter which is connected, if a voltmeter is having a low resistance, then what will happen? Some of the charge might, like the capacitor might discharge, might lose some of the charge. We don't want the charge to flow. We want to keep the charge on the capacitor. That's why the voltmeter should be connected in parallel, and that should not have a low resistance. It should have a very high resistance. So the main reason is that why we prefer a voltmeter to have a high resistance, so that the capacitor does not discharge. Otherwise, if the capacitor discharge, what we calculate and what was originally, that will have a difference. We don't want the charges to flow. A Coulomb meter is charged a resistor with a resistance of 4.6 mega ohm, and it's placed across the terminal and the capacitor discharge. So this is a discharge. The graph is there. The charge shown on the display is recorded, and the graph against the time is plotted as charge against the time graph is plotted. Use the graph to determine the capacitance of a capacitor. So how we can use a graph to determine the capacitor of the capacitance of the capacitor? So the charging and discharging graphs are always exponential change. So Q is equals to Q naught e raised to power minus T over RC, where T is Q naught is the maximum value of the charge, which is stored, or when it is discharging, it is stored one. When it is charging, it will be the final charge. That will be maximum value Q naught. Q is the charge at a certain time interval. R is the discharge resistance. If it is discharging, it will be discharge resistance. If it is charging, then it will be a charge. So we have a capacitor, and this capacitor is discharging through a resistor of 4.6 mega ohm. And we have this device, a coulomb meter is there, which is recording how much charge flow out. And the charge shown on the display record. So in the display record, what is the charge shown to us? That is 26 nanocoulomb. And here we have 10 boxes, 5 boxes equals to 10. So each is representing 2. So this is 52, 54. This is somewhat 56. So maximum is 56 nanocoulomb. And then on the display, we have 26 nanocoulomb. And how much time it took? 10 boxes equals to 4. So each is 0.4. So 2.4, 2.8. So this will be 3.2. So Q is equals to Q naught e raised to power minus T over RC. So the maximum was 56 nanocoulomb. So 56 into 10 to the power minus 9. And the charge which is there shown is 26 nanocoulomb. E raised to power minus T. The time to discharge to this value is 3.2 seconds. So 3.2. R is the resistor through which it discharged. It is 4.6 mega. And C is the capacitance. We don't know. Now we simplify. So this will be 26 into 10 to the power negative 9 divided by 56 into 10 to the power 9 is equals to e raised to power minus 3.2 divided by 4.6 exponent 6 into C. Now to cancel this e, we take ln both sides. So we take ln. So this will be 26 into 10 to the power minus 9 divided by 56 into 10 to the power minus 9. Ln and e will cancel out each other. Like they are anti-functions, so cancel out. So what we are left with, we are only left with minus 3.2 divided by 4.6 into 10 to the power 6 mega into C. So C is our subject. Sorry. So C is our subject. We just cross multiply to work out the value for C. Yes, the function ln and e is important. You have to learn how it can be used. So just use the formula Q is equals to Q naught e raised to power minus T over RC. So just C is near it. You just cross multiply and you will get the final answer. This is one way of solving the question. There's also another way to solve the question, that we can also use the concept of RC as a time constant. Like we have the formula that Q is equals to Q naught e raised to power minus T over RC. When this time is equals to RC, when a capacitor is discharging, it will discharge to 37% of the maximum value. If it is a current, it will be 37% of current. If it is a voltage, 37%. When T is equals to RC. So, means this value will be equals to 37% of R Q naught, or you can also say 0.3 Q naught when you convert into fraction. And this is Q naught e raised to power minus T minus T over RC. Like this RC is called a time constant. The value, this will be the time constant. So we can work out when it will discharge to 37% of its original value. Like say this value is 56. So what is 37% of the 56? So divide by 37 into 100. And using this, you will have the time, like how much time it take to 37% of its original value. First, you can work out this time constant. Like if you don't want to use this whole formula, you can use the time constant. The time constant will be 37% of the original value when it discharged. So check the maximum value of the charge. Let's say it is 55 or 56. So 56 nanocoulomb. So 56 nanocoulomb. What is the 37% of 56 nanocoulomb? 56 divided by 37 into 100. And from that 37%, like 37 into 56 divided by 100. What's the answer for this? What is the answer for this part? When you work out the RC, 37 divided by 100 into 56. So 56 times 37 divided by 100, that is 20.72. Okay. So means what we can do, we can draw a line from 20.72, 20, because this will be 21, this will be about 20.72, and we work out the time. So this is 4.4. So it means this time constant 4.4 is equals to RC, because what is the meaning of the time constant? Time constant, which is equals to RC, it is the time taken by the capacitor to discharge 37% of its original value when it is discharging. But when it is charging, it is the time taken by capacitor to reach 63% of the original value. So it will be 4.4. R is the resistance, 4.6 into 10 to the power 6, and C is a capacitance. So we can divide 4.4 divided by 4.6 into 10 to the power 6. That will also give us the capacitance. So that is another way of doing the same question. Is it clear? So just keep in mind, when it is discharging, it is 37%, but when it is charging, it is 63%. Calculate the energy stored by the capacitor. So how we can work out the energy stored? We know the capacitance is known, and what was the potential? It's not given. So we can use because to know the energy stored in the capacitor, three formulas are there. The energy stored in the capacitor is half Q into V, and Q is equals to CV, because we don't know the voltage, or C is equals, or V is equals to, because Q is equals to CV, or V is equals to Q divided by C. So if I substitute here, so it will be half Q over C. So the energy stored in the capacitor will be half Q square by C. So we just substitute, Q is a maximum charge, 56 into 10 to the power minus 9 square divided by 2. And the capacitance, the answer here, what we worked out, that we will write, so we'll know how much energy the capacitor will store. Because we were not having the voltage, otherwise we can use the first formula. But there's also another formula, that energy stored in the capacitor is half CV square. But that is formula valid if we know the capacitance and the voltage. As the voltage is unknown, so we cannot use any of these two formulas. The third one is like this is not valid, and this first one is not valid. So we use the second one. The next, the notes with the coulomb meter state that the coulomb meter has a much higher capacitance than the charge objects. It is being used with so effectively, all the charge is transferred to the meter. Explain why the charge will be transferred to the capacitor with much higher capacitance. So we have to explain this note here, like so as they already mentioned, like the notes with the coulomb meter state that the coulomb meter has a much higher capacitance than the charged objects. So like higher value of a C is there. So Q is equals to CV, so C is very high. Then the charge object it is used with. So effectively all the charge is transferred to the meter. Like for example, we have a coulomb meter and there's another charge object is there. So if this charge object is like 30 coulomb charge, all will be transferred to the coulomb meter. Why? Because it is having a very high capacitance. So if the capacitance is high, what is the relation between the charge stored? So we have the formula Q is equals to CV. If you have a constant voltage, a voltage does not change. So the charge stored on the capacitor directly proportional to capacitance. So the higher or a greater value of a capacitance, so it means it will store greater charge for the same potential. Like to have the same potential, say this object has a potential of 2 volts. The capacitor and the charge, like it's stored, say this has a capacitance of 10 coulomb, 10 coulomb per volt. So means it can store 10 charges per volt. But because the coulomb meter is having a high capacitance, so for the same volt, it will store more charge because the value of a C is higher. C is proportional to Q and it is inversely proportional to V because the formula is Q is equals to CV. But V is constant. Like if I need 2 volts here, I also need 2 volts here. For the same 2 volts, I can store more charge on the coulomb meter as compared to that of a device. Is it clear, this relation? The data from the graph was obtained by using a video camera to record the column display and replay this frame by frame. State an advantage of using this method. So, what is the advantage of using a camera? So, first thing, like using a camera, we can have multiple points we can obtain from this, like any certain time intervals of the frames, we can know the value. And using a camera, we will have a simultaneous reading. Like when a person is using like a stopwatch is there, so he has to see the time and then he has to read a coulomb meter. But if a camera is there, both the timer, even a timer is not there, but a coulomb meter is there and a camera frames are, we know. So using that, we'll know how much discharge is there every second or every minute or every 30 seconds. So we can have more readings in a given time. These are some advantage of using camera over the um, normal digital stopwatch, and we analyze this capacitor. In question 19, a student is investigating the capacitance. She sets up the circuit as shown. A 6-volt supply is there, a variable resistor is there, and a capacitor. Remember one thing that because there is a variable resistor, so this total voltage 6 is there. What will happen initially? The capacitor, when we close the switch, the capacitor will have 0 volts and this will have 6 volts. But as the capacitor stored the charge, the voltage across the variable resistor start to decrease and voltage across the capacitor start to increase from 0 to higher value. But it will not be like this when the capacitor is fully charged. It will not be like 6 volts here and 0 volts here. That will be wrong. There will be some voltage. So because it cannot have all 6, as there's a variable resistor as well. So this will have maybe 5.9 or 5, then remaining 1 volts will be across. Once even it is fully charged. So if it was only a capacitor and the battery, in that case, the capacitor will have the same voltage as the battery. But there's another component. So even though the capacitor is fully charged, but it will not have the 6 volts because some voltage will be there across a variable resistor. When a switch is closed, there is a maximum current which decreases to 0 over a period of a time as a capacitor charge. Explain why. So initially, why we have a maximum current? The capacitor was not charged. So there was no charge on the capacitor. So there was no charge to oppose the motion, or initially the potential across the capacitor is 0. And the potential across a resistor is 6 volts. So as a result, there is a greater difference in the potential between, as you can see here, the voltage, as I just mentioned, at this point we'll have 6 volt and at this point we have 0. So there is a greater difference in the potential. If greater the difference in voltage, greater the flow of the charges. So as a result, and the capacitor will start to get charged. Once the capacitor will charge, it will oppose the motion. So as the capacitor is charging, the flow of the charge start to decrease. Eventually, there will be the charges will be stopped or not able to overcome. So eventually, potential across the capacitor will be equals to EMF. So the current will be zero. Once the capacitor fully charged, now it will have 6 and this will be 0. So initially what happened? This was 6 and this is 0. When the current is flowing, the capacitor is charging, voltage across the capacitor is increasing and the voltage across the variable resistor is decreasing. And eventually what will happen if the current stop, there is no flow of the charges, then only the potential, the variable resistor, the voltage across the variable resistor will be 0. When the current stop, if the current does not stop, there will be potential difference. And now the battery potential is same as the capacitor, so there is no flow of the charges. That's why the potential across the variable resistor will be 0. The student discharged the capacitor. She sets the variable resistor so that its maximum resistance and is close to it. As a capacitor charge, the student decreases the resistance of a variable resistor so the current remain constant until the capacitor is fully charged. The graph of the current. So what student is doing? Student is maintaining the flow because what will happen? The current is start to decrease. As the current is decreasing, what student is in the beginning, the current is maximum. So student is adjusting this resistance, so maintaining a current. As the capacitor is charging, the voltage is increasing. So V is equals to IR. So as the current start to decrease, why the current start to decrease? Because the resistance of the capacitor is increasing. Like because the charges oppose the motion. So as the resistance of a capacitor is increasing, what student did? Student reduced the resistance of a variable resistor. So the sum of the resistance will remain constant. Because if R1 is decreasing, R2 is increasing, but the sum remain constant. If the resistance remain constant, we have the voltage supply, so V equals IR. So if the total resistance is constant, total voltage is constant, so the current will also be constant. That's how student maintain the constant current in this circuit. So the question is determine the capacitance. The question is to determine the capacitance of the capacitor. So how we can determine the capacitance of this capacitor? We have the formula Q is equals to CV. And the current and time graph, what area under the graph represent? Area under the graph represent the charge stored. How much charge is there? For current and time graph, whenever you have a current time graph, the area under the graph will show how much charge will be stored. What is the value of Q? In this case, it is making a rectangle and a triangle, like this part, or you can use a trapezium. But keep one thing in mind, it is a millisecond. So when you substitute the value, you should take that as, and then you use the formula Q is equals to CV. Maximum voltage will be 6, but what is the maximum charge stored? We'll use area of this graph. You can use a trapezium. So sum of the parallel side, half sum of the parallel side into height, we'll get the area of this and that will be equals to Q. And the voltage is 6, so if we need C, it will be Q divided by V, that will be equals to capacitance. Is it clear? This one, how we worked out the capacitance of this capacitor? The next we have hence determine the energy stored. So how we work out the energy stored? We have the capacitance and we have the total charge. So we can use, even we have the voltage, so we can use E is equals to half Q into V. Q will be the total charge, which we was the area under the graph, and V is the voltage. So when we multiply, we get the answer. Or you can also use energy stored as half CV square. So you have the maximum voltage 6 and the capacitance is there as is this answer. So we'll work out how much energy will be stored. The capacitance can also be determined by measuring the some of the formulas are given in the data sheet, but not all of them. So you have to learn these. Explain how the capacitance can be determined using this graph. So student plotted a graph between. So we have the formula I is equals to I naught e raised to power minus t over RC. If I take ln both sides, so this will be ln I is equals to ln I naught e raised to power minus t over RC. And when in log, when two quantities are multiplied, we write them as addition. So this will be ln I naught plus ln e raised to power minus t over RC. When we further simplify, ln I is equals to ln I naught minus t over RC. If I rearrange the equation, I will write it here. So ln I is equals to minus t over RC plus ln I naught. So we compare with the equation of a straight line, which is y equals mx plus c. On y-axis, if I have ln I, on y-axis I have ln I. On x-axis I have t. So what will be my gradient? My gradient will be minus 1 over RC. So if I want to determine the capacitance, so the capacitance will be equals to minus 1 over R into gradient. That will give us the capacitance. And if I need the maximum current, I will just use the ln, that will give us ln I naught. And I can take NT log to know what is the maximum current. So there are properties of ln and E. Properties of ln and E are there. So I will explain to you basic function you should know, basic concept of ln and E you should have, but it's not issue. I will explain that in the next session. And the next is a capacitor was discharged through 390 ohm resistor. The capacitance of a capacitor is 200 into 2200 microfarad. Explain why the data from the graph would be difficult to obtain using an ammeter, and your answer should include any calculation. So when we work out the value of RC, the time constant, so 390 times 2200 microfarad. So the value of RC will come out 0.86 seconds. Means this is a time, because if it is a charging of a capacitor, if it is a time, a capacitor will take 63% of to reach 63% of the maximum, and if it is a discharging, it will be 37% of the maximum. So the RC is 0.6 0.86, that is the value for RC. Usually the time for a fully discharge is usually 5 times RC for a fully discharge. So 5 times RC, so 5 times into 0.86, that will be about 4.29 seconds. So 4.29 for a fully discharge. And for this capacitor, if you see the time interval, so the question was why it will be difficult to use this graph